Okay, welcome everybody. And today we want to talk a little more about work and its relationship to line integrals, and then talk about conservation of energy and see how we can derive it from what we know about line integrals. Okay, so we think about force as being given by a vector field, capital F, and we want to know the work done when a particle moves along a smooth curve C under the influence of this force field, capital F. So we'll parameterize our smooth curve by the functions x of t, y of t, z of t, and we'll say the starting points and the ending points are where r of a and r of b. So in other words, t goes between a and b. And as we saw in a previous video, the work is defined as the line integral of f dot dr. And then how do you compute the line integral? Well, you use the parameterization of the curve. You evaluate f along the parameterization. And then dr means r prime of t dt. And you have a dot product there. So let's make sure this makes sense. This is a vector. This is a vector. You take the dot product, you get a scalar. That means we have a scalar valued function of t, which we can integrate by calculus 1 methods. And the limits on t are used here because that gives you the starting and ending points for the curve. Okay, so that's what you already know. Now let's do an example. Suppose we ask the question, what is the work done by a gravitational field when a particle moves along a curve from the point 111 to the point 323, and as I said, under a gravitational field. So that means a gravitational field, if we put the bigger particle and say the bigger particle has mass capital M and the smaller particle has mass little m, the one that's moving, and we're going to take this big particle and we're going to put it at the origin, okay, of our coordinate system. Then we can write the force, the gravitational field, as little m capital Mg, where this is the gravitational constant associated with the object with mass capital M, times r divided by r, length of r. Okay, so that's an inverse potential. Okay. Okay, and now if you remember, this is a conservative vector field, and here's the potential. Okay, so the potential for it is little m capital M times its constant, gravitational constant g, times the length of the vector r, that is the square root of x squared plus y squared plus z squared. And if you don't remember that, it's really easy to check. Just take the gradient of that function, little f, and you will see clearly that it is the potential for that function, for that vector field, capital F. Okay, so what is the work done when we move the particle along that curve C in this gravitational field? Well, we know from definition that is the integral over C of f dot dr, and that was discussed in one of the earlier videos in this module. But since f is conservative, that's the same thing as the integral over along the curve C of the gradient of little f dot dr. Okay. All right. Which, remember, by the fundamental theorem of calculus for line integrals, when you have something of the form gradient dot dr, then that you evaluate that by f evaluated at the ending point of the curve minus f evaluated at the beginning point of the curve. So for us, we just know those 2 points. We don't even know which curve, much less a parameterization for it. So we evaluate f at 323 and then subtract the value at 111. Okay, and so to get that, we just plug into this formula for f, and you see that you get the square root of 1 over the square root of 9 plus 9 plus 4, so that's 22. Okay, and then at 111, you get, pulling out the constant mmg, you get 1 over the square root of 3. And that's independent of whatever path you took to get between those 2 points. And that's consistent with what we learned earlier in this module, because you know that if you have a conservative vector field, then it's independent. The line integral along between any 2 points is independent of the path you chose to get there. Okay. All right, so now let's start to talk about conservation of energy. Okay. Okay, so suppose I have a particle is moving along a curve C. Parametrized. Then I'm going to assume it's a smooth curve. Parameterized by R of t is x of t, y of t, z of t for t between, say, t1 and t2. From the point A, let's say, which is x1, y1, z1, to the point B, which let's say is x2, y2, z2. So those are 2 fixed points in space, and you have a particle moving along this curve in a vector field capital F. Okay. Okay, and so capital F is our force, and it's given by a vector field. Okay, so what's the work done by this particle as it moves along this, from this point to this point in this vector field? Okay, so let's, this is, the work is the integral from, as things go from the point A to the point B of F dot dr. Okay, and that is equal to, I should say the curve C here, because I haven't parameterized anything. Okay, and so that's equal to the integral from T1 to T2 of F of R of t times R prime of t dotted with R prime of t dt. Okay, all right, but now notice that this is the position vector for the particle when it moves along the curve. What's the velocity vector? The velocity vector is v of t, which is R prime of t. And if you wrote that out in components, that's x prime, y prime, z prime. Okay. And what's the acceleration vector? So a of t is v prime of t, which is R double prime of t. And so that's x double prime, y double prime, z double prime. Okay. Okay. So notice R prime, so I can write the work as the integral from T1 to T2 of F of R of t dotted with V of t. And that shouldn't be there. dt. Okay. On the other hand, by Newton's second law, the force is equal to the mass times the acceleration. So this is m times dv dt. Okay. So I can replace the force by m dv dt. These are vectors. So the work is the integral from T1 to T2 of m dv dt dotted with v of t dt. Okay. And now you notice, if you stare at that for a minute, that this is equal to m over 2 integral from t1 to t2 of the derivative with respect to t of v of t quantity squared times dt, right? Because if you differentiate v of t squared, what do you get? You get 2 v of t, but you're differentiating a vector. So how did that differentiation rule go? Then you get dotted with v prime of t, which is exactly what you have here because the 2 cancels in with the 1/2 out in front. Okay. All right. But now this, let me rewrite that just a little bit more. So that's d of v of t quantity squared dt. So whoops, no dt. The dt's have canceled. Okay. So that's like saying, what's the integral of du? Well, you get back u. So in other words, we get back the velocity squared. So I get m over 2 times v at t2 squared minus v squared at t1. But the mass times the velocity, the m over 2 times the velocity squared is the kinetic energy. And the point T2, when you're at the point, when you're on the parameterization at T2, you're at the point B. So let's write this as the kinetic energy at B minus the kinetic energy at A. Okay. So what we just showed using Newton's second law and the fundamental theorem of calculus here says that the work is the kinetic energy at the ending point minus the kinetic energy at the starting point, independent of whichever path you took. Okay. All right. So now let's, okay. So that was for any vector, any force field. Okay. But now suppose capital F is conservative. Then there is a potential little f such that capital F is the gradient of little f. Unfortunately, as usual, mathematicians and physicists do things in a slightly different way. Just, I think at some point, people began to do that just to confuse each other. Just kidding on that. But anyway, it seems to work out that way. So this is what a mathematician calls a potential. But the physical potential, so to a physicist, F is minus what they call the potential, the one that leads to the potential energy. So gradient of, so that P, little p here is the potential for potential energy. In fact, that's where the word potential comes from. Okay. So it's, we say the gradient of F is capital F and we call little f the potential. They would say minus the gradient of P is what you get for a conservative function, and then call P the potential. Okay. So F conservative says that the work, which is the integral over the curve of F dot dr, is equal to the integral over the curve of minus gradient P dot dr. Okay. So by the fundamental theorem of calculus for line integrals, we get the function minus p evaluated at the endpoint, which we call b, plus the start minus the value, which is minus p, at the starting point. In other words, the work is the potential at A minus the potential at B. Okay. All right, so that's the potential energy at A, and this is the potential energy at B. Okay. All right, so equating those two things, gives us that K of B minus K of A is equal to P of A minus P of B. Okay. And I remind you, this is the potential energy at B, and likewise the other one is the potential energy at A. So equating both those things that we got here and at the bottom of the last page for work. All right, so now rewriting this just a little bit says that P of A plus K of A is equal to P of B plus K of B. That is the total energy at A is equal to the total energy at point B when there's no other external forces. It's only the only force acting on it is this one force, capital F. Okay, so think about what that says. It says the energy at the starting point, total energy, is the same as the total energy at the ending point. That is, energy is conserved. Okay, and to make that go, we needed this hypothesis that F was conservative so that we could use the fundamental theorem of calculus for line integrals to get our potential energy term. So the fact that you had a conservative vector field was critical for getting the potential energy part of this calculation, whereas the other part of the calculation for kinetic energy is always true. Okay. All righty, so that's conservation of energy. And that's it for now. See you next time.